Okay, so in this video, we want to find the area of the exact same region as in our previous video, but providing now a much more elegant solution obtained by covering up the region not with two separate sets of vertical rectangles, but by a single set of horizontal rectangles. So we draw, as always, a generic rectangle, now chosen to be horizontal. The width of our rectangle is an infinitesimal change along the y-axis, so it is of course given by dy. Since we have a generic horizontal rectangle, its position is an arbitrary y value, call it y, and as always, all we need now is the length of the rectangle to obtain the corresponding area. If you notice, the length of the rectangle is a line segment along the x-axis, so we need the larger x value, of course in terms of y, and the smaller x value, also in terms of y. And why will this lead to a more elegant solution than in the previous video where we used two separate sets of vertical rectangles? Well, if you recall, because going with vertical rectangles introduces a shift on the curve on top, going from 4x to 5 over x minus 1, this is the reason why we had to use two separate sets of vertical rectangles, because the curve on top changes from 4x to 5 over x minus 1. But if you look now at a horizontal rectangle, to get the length of the rectangle we do the right-hand point, so the curve on the right, minus the left-hand point, the curve on the left. But no matter where we place this generic rectangle in our region, the curve on the right is always 5 over x minus 1. The curve on the left is always y equals 4x. So with the choice of horizontal rectangles, we only need one set of rectangles, as the measurements are always the same across the entire region. So let's start with the easier point. So now at the left-hand point of the rectangle, we are on the curve or the line y equals 4x, and we have to solve for x in terms of y. This is very easy. Divide by 4. So x is a quarter times y. So we have the value of the left-hand point of our rectangle in terms of y. Same thing for the right-hand point, but now at the right-hand point of our rectangle we are on the curve y equals 5 over x plus 1. So we now have to solve in this equation x in terms of y. Well, the first step is to add 1, so 5 over x equals y plus 1. If you invert both sides, then x over 5 is 1 over y plus 1, multiply up by 5, so x is 5 over y plus 1. And we now have the right value of x of the right-hand point as a function of y. So as always, the length of the rectangle will be, since it is a horizontal segment, the bigger x value, 5 over y plus 1, minus the smaller x value, 1/4 y. So now we can find the area of the rectangle, being the length of the rectangle times the width. So the length of our rectangle is 5 over y plus 1, minus 1/4 y, times the width given by dy. So this is of course the area of a generic infinitesimal horizontal rectangle. But to obtain the entire area of the region, we have to sum the area of each infinitesimal rectangle, but now be careful. The rectangles are positioned along the y-axis, and they cover up the region going from y equals 0 all the way up to y equals 4. Now, of course, we evaluate using the fundamental theorem of calculus. Antiderivative of 5 over y plus 1 is 5 ln of y plus 1 in absolute value, minus, power rule here, y squared over 2, 2 times 4 is 8, so minus 1 over 8 y squared. And of course you can easily verify, differentiate this with respect to, of course, y, you get 5 times the derivative of ln 1 over what's inside, so 1 over y plus 1, check, times the derivative of y plus 1, which is 1, so this works out. And if you differentiate this from the power rule, you get 2 over 8y, which is a quarter y. And we, of course, evaluate from 0 to 4. So replacing y by 4, so 5 times ln of 4 plus 1 is 5 ln of 5. Minus 4 squared is 16, over 8 is 2. And then minus the antiderivative when y is 0. But if you replace y by 0, you get 5 times the ln of 1, which is 0. Minus 0 squared is 0, so you get nothing else. So the area, as before, is 5 ln of 5 minus 2, which we know is approximately 6.047. And the reason, again, why this was a more elegant solution than in our previous video is that we only had to set up a single definite integral to return the entire area of the region. And this was because the measurements for our generic horizontal rectangle did not change across the entire region. So always look at it this way. When you look for the area of a region in the xy plane, if possible, it may not always be the case, but if possible, try and choose a set of vertical or horizontal rectangles that will lead to a single definite integral. And that's it.